afternoon. My name is Gyan, and I'm delighted to be here, seeing so many familiar faces from PCIM in Nuremberg, PCIM in Asia. So thank you for coming here. Looks like there's a lot of commitment to build semiconductor and power packaging ecosystem in India, and we truly appreciate it. All right. So my talk is around sintering, 4 different parts. I'll start out with taking a look back at the EV drivetrain, how it has evolved with power electronics. Oops. Then we will touch base on sintering. Thomas touched lots of aspects about sintering, the process, but I'll go in more on the materials and the reliability side of things. Then I want to spend a little bit of time on 2 use cases which are beyond the traditional die attach, which are related to module attach and packaging for discretes. Since essentially for EVs, even high-end EVs, the die attach issue for reliability, lifetime, and thermal resistance, that use case has been solved, right, with sintering. But so the frontier for improvement in reliability has moved to different layers, and those are the layers we are addressing now with MacDermid Alpha. So, okay. But a quick detour before we start with the talk. I wanted to talk about my company. What do we do? So what we have on the right is a cross-section of an advanced package that's like a logic device, CPU, GPU, something that drives the computing part of the data center. And on the right is a traditional power QFN package. And what I have done is mark different layers of connections and interconnects and metallization layers where we play. So starting out from copper damascene for transistors, all the way to RDLs, vias, copper pillars, plating on copper pillars, and on traditional packaging side of things, die attach, solder materials for board level assembly. So we have this suite of materials that go essentially from all the way from chip, semiconductor wafer, all the way to the box. Okay, so we believe it's a unique capability in the industry where we play across the system, where we understand not just the materials but the processes and how they interact with each other. Okay, so if any of these things are an unmet need or a pain point for you, I'll be very happy to talk to you offline about any of these materials. All right. So the next slide, this is about a trip down the memory lane, just because I want to sort of congratulate ourselves on how far we have come in EV space between 25 years. So starting out in late 90s, I don't know if too many people are familiar with or not, Ford launched an EV called EV1. It used to run, of course, on IGBT discretes, but lead acid battery, okay? Used to go about 125 miles or so. But the real big leap came from, of course, Tesla. That was Model S around 2012 or so. It was again custom built with discrete IGBTs, 84 of these or 96 of these with 2 different dies, the IGBT and the diode. Just after that, there was a big revolution. I call it revolution because it was a big change, a step change in power density of inverters using sintering, done at Continental in Europe. That was used for very high-end cars, hybrid as well as full EVs, across several brands. Then the real mass adoption, of course, came with Tesla Model 3 around 2017, which transitioned from IGBTs to silicon carbide MOSFETs. Okay, so it was a step change when it came to the power density and reliability, and also modularity, right? So you could have different power level inverters by changing the number of MOSFETs, single switches. These are single switches, not traditional block modules. So that was a big change where they were shipping these things out in millions. And then over the last few years, we have seen some high-end car makers in China really push the envelope with power density, with with very specialized stack, with very advanced packaging, with silicon carbide, and of course pushing the voltage envelope further from 650 volt devices to 1200 volt devices because they are using high voltage battery. So on packaging side of things, things transition from simple solder to wire bonding to sintering, and moving beyond sintering at the die level. Now the sintering is moving across the levels from the top side attach where the clip or the wire bond used to go, also to the module attach. And I'm very proud to say that our company, MacDermid Alpha, has been a partner in this journey at all the stages with all these companies which are shown here. Okay. So what's this big deal about these materials and the sintering? So essentially, these materials that we are talking about, these are materials that form layers and interconnects in the stack. And these layers, they perform three key functions. They provide power, they help in heat dissipation, and also they keep things together, right? I mean, in an automotive device, high temperature with the shaking and the vibration and the CTE mismatch, you need to have materials that can withstand these higher conditions, these very harsh conditions. And ability to do that, on top of that, doing it with the smallest footprint, with smallest bill of materials and high power density, so that we can have high efficiency as well as reliability at the same time. So the role of interconnects and joining layers is very often ignored in power electronics or packaging in general, but I just wanted to bring that up. So about sintering, how's it all related to sintering? So sintering essentially is the process of taking powders and joining them together with heat and pressure to form one structure. But the key here is that all this happens at temperatures which are far below the melting point of the material. So silver melts at 960 plus, but we do processing around 250, 230, somewhere in that range. Okay, but the reason it stands out is after the sintering is done, what you get is a material which is essentially pure silver or copper in copper sintering case, and these materials, they essentially stay solid all the way to the melting point. So you have very high range of operation when it comes to temperature. You can tune the modulus of the material by changing the size of the nanoparticles in process conditions, and also they have very high bulk thermal conductivity, upwards of a couple of 100 watts per meter Kelvin, so that you can have lower thermal resistance and have higher power density. All right. And here, so why do it? So here I bring an example of an EV inverter that was sintered at two different levels. So where the top side, the clip was sintered with the material, with the sintering, the silver material, as well as the die bottom. And this was presented by the customer in an open forum. What they saw was a 10x improvement in reliability over tin silver solder. And here we are not even talking about the improvements you get in power density with smaller materials, smaller amount of packaging materials. Then you can have smaller semiconductor area, operate your device at higher temperature, and also at the same time have smaller cooling system. Okay, so there are added benefits that come, which are system level benefits from using this technology. There is another example which I won't go into detail, which is in public domain, has been around for a decade, which is die attach with sintering for a rail traction module. Okay, and I believe this was also done with silicon carbide. So now I will change gears and go into two use cases of sintering. The first one being module attach. So module attach essentially is taking a module and attaching it to a heatsink. In this particular case, we're talking about aluminum, which is the extreme case for reliability because of the CTE mismatch between aluminum and the ceramic substrate used in the power module. All these surfaces have been plated with silver. On the left side is some information on the parts that were sintered. So we used a couple of different sintering pastes and with different bond line thicknesses. Processing was done around 230 degrees Celsius, very typical for sintering. On the right-hand side, there's more information about soldering. We use different alloys, but kept the same bond line. Okay. And some initial scanning acoustic microscopy was done to make sure we have gotten good joints. Okay. First reliability test that we did was thermal cycling, and I just wanted to make sure, make note of the conditions. So what you have are the conditions which are much harsher than you would see in a standard like AQG324, which is a standard for automotive power reliability for power modules. So it has much more extreme temperatures and longer dwell time. And just because the data on AQG324 standard conditions has been published and it's validated. There are millions of cars running out there without any issues, but our customers are pushing the limits. They're asking for reliability, which is much more higher than what the standard is asking for. Okay, so that's why we are pushing the limits. So what you see with sintering is after 1,000 thermocycles, you start seeing delamination, and after about 1,000 cycles, you see delamination, which is of the order of 25 to 42%. But in real conditions, if you were running it with AQG324, it would be less than 5%. Solder, of course, fared much worse. They were getting very large delamination within a couple of 100 cycles. After 1,000 cycles, even the best parts had more than 80% delamination. Okay, but the real proof of the pudding is when you do the power cycling, which was done with AQG324 standard, 30 seconds on, 15 seconds off. And the best sintered sample, they survived 200,000 cycles even before the 5% VDS on limit was reached. And at that time, more than 97% of the area was intact, and there was no degradation in the sinter layer. The failure that was traced was back to the epoxy molding compound, not the sinter layer. On the solder side of things, here you see the best solder reached the limit of 5% VDS on with only 40,000 cycles, and by that time, about 60% of the area had delaminated. Okay. Before I move on to the next use case, I just wanted to talk about plating. We at MacDermid Alpha also supply plating solutions that are very synergistic with sintering. And as you can see, plating of these surfaces is very critical to make sure you get good corrosion resistance as well as good reliability, both from performance side. So if you have, if you want to talk about a synergistic solution that works for high reliability, both for plating the heat sinks as well as assembling the devices for the inverter, we will be very happy to talk to you. Okay. So the last piece of my talk is related to sintering for discretes. Okay. Sorry for the big chart here, but essentially it's a process of applying the sinter film right on the wafer. Okay, so you apply a sinter film on the wafer, you apply the dicing film, then you go through the dicing step. So you have a part which is already attached with silver sintering film that you can pick and place and sinter offline. Okay, so that takes away the responsibility of applying sintering from a packaging house with the wet paste to a supplier like us, where we control the bond line for you and give you it in a film format, which is ready to laminate and dice and assemble. But one key thing here is the device yield is very important, because if you are working with MOSFETs or diodes, silicon carbide or silicon, it's important to have, there is a certain threshold of yield of devices on the wafer before this thing makes sense. But I'm very happy to say I've been surprised lately with the kind of yield our customers are reporting with even silicon carbide MOSFETs on their wafers. So this thing is becoming mainstream now. There's a lamination step, which with the sintering film and then the dicing tape. The next step is related to dicing, where we have tried different dicing saws with different blades, different feed speeds, that sort of stuff. One thing I forgot to mention here was the choice of dicing tape is very critical. And we have spent a lot of time weeding out a bunch of dicing tapes that are not compatible with our system, and we can help you choose the right dicing tape based on your device and the size of the device. And then finally is the die attach step, which can be done in 3 different ways. So starting from the right, you can do sintering in situ. So soft solder die bonding with high lead soft solder. You can equip with high bond force head, and you can sinter the device right on the soft solder die bonder as you put it down, so that there is no need for an offline sintering step. Or on the extreme side, you can place a tacking agent on your substrate, pick and place dies very, very fast, and you can get UPH or throughput, which is upwards of 10,000 parts per hour. Okay, and somewhere in between, you can also do hot tacking, where you have to heat the part both from the top and the bottom, meaning the substrate as well as die top, where the UPH is in between. So what I mean to say here is there are a lot of options depending upon the equipment availability, and we can help you through the process. On this slide, I have a couple of videos just to show you that we have done the process a few times with a couple of customers end to end. This is an example with a TO263, a large device where we have been able to do upwards of 10,000 parts in 1 hour.
Yeah.
Okay, so I'm almost done. So here's the big picture, literally. For 1 million parts per day, if you were to use soft solder die bonder, you would need about 24 of these soft solder die bonders. But with our wafer level sintering film, you can do 4 epoxy die bonders and 1 sinter press, and leave out a lot of space, which can be used for other purposes, or essentially result in lower cost. So before I finish, I wanted to circle back to the EV growth. So innovation in power electronics has really helped us keep up with the inflation over the last decade. And I believe the future is even brighter with wider EV adoption for sustainable planet. Let's make it happen, and we are here to help. All right. Thank you.